because this is the sum of all solved salts of the alkaline earth metals in water. So the water hardness is the sum of all solved salts of alkaline earth metals in water. The most important are those from the calcium, so the calcium 2+ ions, the solved ions, or the magnesium 2+. Those are the most important. When we talk about water hardness, I think you heard about water hardness. Do you have some own experience on that topic? I think you can see it. Are you living in Pfarrkirchen? Who of you is living in Pfarrkirchen? Or nearby in Lower Bavaria? Do you have a water cooker at home for tea or for whatever? No. Yes. Sorry? Just a pen. But when you cook water from time to time, what can you see? A white coating inside of the water cooker or even in the pan. Yeah, it is. It is a calcium mineral which is formed when you evaporate. So water cooking, yeah? And a part of it, we call it temporarily hardness. You cannot remove. And the hardness, the temporary you can remove, and the permanent you can't remove. So there are different types of hardness, and at the end, they are all different salts of calcium and or magnesium. Because when the water is cooking, every time a little of that water is evaporated. And you have some conversion of these calcium magnesium salts in the cooking process. A part of it remains as solved ions, and the part of it, which is temporarily, is precipitating. And that builds a surface coating, a white coat of that carbonates or sulfates. These are the carbonates on the surface. And we will have a look to that, what happens in this process. The temporary hardness is the carbonate hardness. We have the carbonates and we have the sulfates of those alkaline earth metals. The temporary hardness is the carbonate hardness. What happens? We have solved ions of these alkaline earth metals. Let's have a look to the calcium. And we have the hydrogen carbonate. What is the charge of the HCO3? When you just look to the HCO3, there is a charge of this ion, and you should calculate it. What will be the charge of this one? +1. Why? What is the oxidation number of oxygen? -2. So -6. Please keep in mind. What is always for the hydrogen? +1. What is always for the carbonate the maximum? 4 plus 1 plus 4 plus 5, but we have -6. What is the charge? -1. So how many of these ions are needed to have a not charged salt with calcium? Calcium is in the second group here. So what is the charge of calcium ions? Plus what? 2. So how many are needed of the hydrogen carbonates? 2, of course. Because we have 1 negative charge, here we have 2. So it must be balanced, having 2 of them. And please be careful, and everything can be calculated by looking into this table of periodic elements, so the periodic table of elements. And more or less, in most of the cases, you can figure out what is the charge, what is the oxidation number, everything. This is our tool. And you will find most of the info needed in here. So that's what we have in water. It's in form of solvated calcium 2+ and hydrogen, what's the name in English? Hydrogen carbonate, hydrogen carbonate ions. Now this is the hydrogen carbonate. Ion. And that's, of course, the calcium 2+ ion. And now we cook our water. We have it in water. So plus H2O and delta T. We cook it. Then automatically a process happens. And we have the formation of calcium carbonate, CaCO3. The carbonate, of course, when we take away the proton here, then we have 2- remaining charges. So then we have a 1-to-1 ratio to the carbonate. The CO3, 2-. And CO2 is emitted as gas, it's a gas. And we will have water which is remaining. When we look to the oxidation numbers, we have +2, we have -2, we have +1, we have +4. Here we have +2, we have -2, we have +4. Here we have -2, we have +4. Here we have +1, we have -2. So now have a look to this. Is that a redox reaction? Have a look to the overall equation. Is there a redox process? Very good. No redox process. No change. We have +2, +2, +1. We have for +1. We have -2 for all oxygen, -2. The carbon +4, +4 on all on the left and right side. So there is no transfer of electrons. So no redox. This is just a rearrangement of the different forms of ions. The carbonate is precipitating, and that builds the white surface in your water cooker. The good thing is, afterwards, the water you have to drink in your tea has a less hardness. But it's not a problem to drink hard water. It's even healthy because in our body, we need carbon, we need calcium and magnesium for our bones. The bones are built out of different magnesium and calcium minerals. So it's not a problem. The thing is, you have a coating of your cooker with the carbonate, this white surface. And this coating has a very low heat transfer. So it doesn't allow heat transfer very easily. So if you like to cook further on water and your thickness of this coating is increasing after each cooking process, because from the hard water, you have the precipitation of the carbonate, then you have a thick layer, and you need to cook to heat up the water in your pot. The heat transfer is very low, so you need more energy to cook your water. And the bigger problem is when you think about you have a closed system. You have a closed system where water is in, and a lot of these calcium carbonate is forming a big, thick coating inside. And that's a boiler. You like to heat up water for some industrial processes in there. So you heat it up, delta T, from outside. You have something, a heating system outside. But the heat transfer is decreasing when the thickness of this coating is increasing. And then by accident, you have some porous part here because it breaks down immediately because the water starts to cooking. There's a movement, but you have to add more and more and more energy. So you have a very hot surface because you need quite a lot of power to heat up the water in there when there is a thick layer. And here you get a hole in the surface. Immediately, a few hundred degrees Celsius hot surface gets into contact with cold water. What could happen is steam explosion. Immediately, water starts to cook, and the whole closed system explodes. And this happened in previous times, sometimes, and people died because they were nearby. They had to cook the water or to heat it up in this boiler. Didn't know about that surface. And then it broke down the surface on one point. Immediately water cooked. When water cooks, you have an enormous expansion of the volume. And that means the pressure increases dramatically in that closed system and it exploded. And people died. Hopefully you won't die in your kitchen. So what do you have to do from time to time? You have to clean up your cooker, your water cooker. What are you doing? Sorry? Vinegar, for example, yeah? Or citric acid. An acid solves the carbonate, and then you clean it to have a fresh, new metallic surface, allowing a better heat transfer, and of course, no problem further on. But you have to do it from time to time when you have very hard water. And here in Pfarrkirchen, we have very hard water. So a lot of carbonates and even from calcium and magnesium are in there. And so you might have to clean your cooking devices quite often. So in a boiler, for example, the heat transfer is decreased because you have here these carbonates, the calcium carbonates, they precipitate. and they build a surface coating that is a white layer with a very low heat transfer. And that's the problem. So in a boiler, the heat transfer is decreased. Decreases. In a boiler, heat transfer decreases. And that means steam explosion can happen. So that is called temporarily, because when you cook it, the water itself, it's getting less hard, because part of the hardness is precipitated on the surface of the cooker. What's the problem? This one? White, not black, it's white. Not black, white. That word means white layer with a very low heat transfer. White, yeah. So this is the temporary hardness. When we talk about temporarily, yeah? Sorry, I didn't get it. It's very hard, yeah? No. If you want to drink tea, some people say the tea has more aroma when you have a not hard water. But it's related to your health. It is not a problem, because you need these ions in your body to build the bones. You have a risk of what? Yeah, but yeah, you normally are not drinking 4-liter water of very hard water every day, or do you? Yeah. So, well, I think that the problem is not so big. The bigger problem is if you drink a deionized water. Yeah? Because then you resolve all the ions in your body when you drink a lot of deionized water. It's always, you have always to think in a kind of chemical balances. And if you already have quite a lot of ions in the water you drink, the process will be from the water you drink, there will a movement of the ions into your body, because here in the water you have quite high concentration. If you drink a water without ions in, the deionized, the process is reversed. You will have a solvation of ions you have in your body in the water. And that could be a bigger problem, because you need a lot of ions in your body for a lot of biological processes. For example, the sodium kalium pump in the cells of all of your organics in your body. There's a different osmotic pressure which relates on the concentration of ions in the different solutions outside the membrane or outside the cell and inside the cell. And there is an osmotic pressure, which is related to how do we have outside a higher concentration of ions or inside, or vice versa. And then ions can move through the membrane into the cell or out. And this is especially very important in the case of kalium and sodium. And this is called the kalium-sodium pump, the ion pump in the body, where the different osmotic pressure, we call it osmotic pressure, moves ions in and out. And this is what you need in a lot of biological processes in your body. So I won't fear too much about hard water drinking. But sometimes it tastes better if you have not so hard water, especially if you are really a tea drinker. If you are removing ions from your tap water, there are some ion exchanging filters. We have it in the lab as well, to be sure that we have deionized water for chemical analytics. Sometimes we need really pure water. We deionize it. And similar systems you can buy as filter to remove the hardness in your tap water. But then you have to keep sure that there is no biological fouling or whatever in the filter system, which creates a bigger problem than just having a lot of calcium ions. If there is too long period of not rinsing the filter with fresh water, and it has a temperature 20, 30 degrees, bacteria can come in and grow, and then you have a lot of bacteria in that water you want to drink, and that's the bigger problem. So here, be careful. Let's now distinguish. Temporary hardness, please keep in mind, that's the carbonate hardness. Then we have, and we can remove it, but via cooking. The problem is the surface, the precipitation, and then the decrease of the heat transfer. But the water itself has less hardness afterwards. The permanent hardness, you cannot remove via cooking. And the permanent hardness are the sulfates of the alkaline earth metals. So the calcium sulfate, not the hydrogen carbonate or the magnesium sulfate. Here, training again, -2. They always have +2. So what is the oxidation number of the sulfur? Zero. -2 times 4 is -8. So here I have -8 and I have +2. So +6 must be. Please be careful. It's the same in here. +2, -2 times 4 +6 for the sulfur. That is even the highest oxidation number for sulfur, because sulfur is in the 6th group. The maximum for the oxidation number is +6. That is all repeating training of that what we already learned in a few lectures before. So it is not possible to get rid of these sulfates via cooking. And that's why we call it permanent hardness. Of course, with an ion exchange filter, we can remove, but not via cooking. So the alkaline earth metals are relevant. They are the carbonates, magnetite, dolomite, fluorites, and they are relevant in the building industry as chalk, slate lime, plaster, and very important because they form the hardness of water temporarily as carbonates. We can get rid of them via cooking with the problem of these surface coating. We have to get rid of the coating as well from time to time. And we have the permanent hardness built out of the sulfates of these alkaline earth metals. Then we get along to the third group of the periodic table of elements. So the next one is 3 metals of the third group. The third main group we have to add. We have the first, the second, and the third main group. Now, what are you remembering when we are here in the third main group? Are all of them pure metals, or do we have here something different already in the third main group? I think we talked about that. Where are the metals and where are the non-metals in the periodic table of elements? Where do we find the metals? So here we have all the metals, here we have all the non-metals. And what is this line here? Yeah, this is what we call it, it's transition, not transition metals, it's half metals. We call them half metals. So starting in boron, that's not a pure metal, it's a half metal. Silicon, it's a typical half metal. Arsenic, tellurium. So here, this is on the right top, non-metals, on the left bottom, metals. This is the transition, so half metal. So the metals in here in the third group are aluminium, gallium, indium, thallium, not boron. So boron is a half metal. And aluminium, gallium, indium, and thallium are metals. These metals here are not noble. So they are not existing as elements or in elementary form in nature. Sorry. So they are not noble, so they are not existing as pure elements in nature. what is the oxidation number of those metals in the third group? What is the typical oxidation number of them? It must be +3. So the typical oxidation number is +3. Aluminium, we already had it. Normally, it will be oxidized to form aluminium oxides, but the aluminium oxide is coating the aluminium, and the oxidation number in the aluminium oxide is +3, so Al2O3. So aluminium is important, the most important in this group. Aluminium. Most important in industry. That is the aluminium. And in nature, we don't find aluminium as pure element. In nature, so the occurrence is we find it as cryolite. That's the name of that aluminium mineral. And the formula is Al. Al, sodium Al3, sodium 3Al, hexafluoride. Well, again, -1 because this is one of the halogens. So 6 times minus, 3 times plus, +3. -1, +1, so here +3 remains. Others in nature is bauxite. Here the formula is AlOOH, aluminium oxide hydroxide. Again, here -2 + 1, -2. So here -1 remaining, -2 +3. Bauxite. And even aluminium OH3 sometimes is a mixture of the oxide hydroxide and the hydroxide itself. We learned about the aluminium oxide. That is Al2O3, which covers the aluminium and protects from further oxidation. That is now discussed quite intensively. So for us in the third group, the metal which we should keep in mind, which has a relevance, is aluminium. Now go on in the fourth group, metals of the fourth main group. when we look to them remaining again, these transition area, so silicon will not be, carbon of course is not a metal, it's already above, it's a non-metal. Silicon is a half metal, so even germanium already counts to the half metals. This is more an area. The real metal which can be found is tin and lead. Lead and tin. Lead, you know, it is a heavy metal, one of the heaviest metals. So here we have to distinguish between half metals. So silicon and germanium, maybe in the half metal industry, you already heard about them, they are half metals. Silicon is used for production of wafers for chips in computers. Silicon is needed for the production of PV system, photovoltaics. We will talk about that in renewable energies technologies. And germanium is even a half metal. Carbon is a non-metal. So the only metals in this group is tin and lead. Typical metals. What is the oxidation number of the fourth main group? +4. But sometimes we even have +2, as you can see in here. The fourth main group, we have tin and lead. And you see both of them, +4, +2, +4, not so often even here more +2. The +2 is what remains when we take away 2 electrons is a full d orbital. So +2 leads to the full d orbitals. +4 leads to full s. Even the s orbitals are away. So here we have those 2 oxidation numbers, possible +4 and +2. And one of these very important compounds where we have here to talk about is here in the area of the half metals is the silicon dioxide, SiO2. Silica. Lead we already talked about in the lead acid battery. Well, going on, the fifth is the metals of the fifth main group, 5. Here we don't have too many. When we look to our periodic table, the transition area, then we already have half metals, arsenic and antimony. The only one is the bismuth. So here, arsenic and antimony are half metals in the transition area here. And the bismuth is the only metal, pure metal in the fifth group. So arsenic and antimony, half metals. and the bismuth is a pure metal. And these, which are on the top of the fifth group, nitrogen, phosphorus, are nonmetals. Sixth group or sixth metals of the sixth main group. Again, look to the periodic table. In the sixth main group, it's here. We are in the transition area. The only one which is really a metal is polonium, and polonium already is radioactive. Tellurium is a half metal, even selenium. Selenium is a half metal, tellurium is a half metal. That's a metal, but it's radioactive. The main oxidation number is +4. It could be +6. So selenium and tellurium these are half metals. And polonium is a metal, but it's radioactive. It's a radioactive metal. That means it's not stable. It underlays the radioactive decay. Just the principles which are possible. We have alpha, beta, and gamma. And to know about these principles, you should know the main representatives in those groups as metals, as aluminium, for example, lead, for example, silicon. It's not a metal, but it has a big relevance in industry as half metal. So some of them which you really might need in your professional career later on. And I think you can imagine which are the most important. And of course, you should evaluate what is the oxidation number. Should be able, what is the maximum or what is the typical oxidation number. If you have to create some chemical equations, redox reactions, whatever, you have to look to the periodic table, figure out in which group what could be the oxidation number. What could happen. So now we talked about the metals. In the seventh group, we don't have any metals anymore. Here, halogens and noble gases. So no metals anymore. So we don't have to talk about metals in those two groups. But we did not talk about the biggest group of metals, the transition metals. So this is the last point in here, the transition metals. So here we fill up the d orbitals. We know. And so here those in the beginning, they are what we call normal metals. The rest on the right side, all of them are heavy metals. Scandium, yttrium, and titanium here, these are normal. The rest is, well, remember it, more than 5 grams per cubic centimeter. So heavy metals. So scandium, yttrium, titanium, we call them normal metals. All others, the rest in this transition area, are heavy metals. They have high melting points. And very high cooking, boiling points. And please remember, I think it was chapter 3.5, the metallic type of bonding. I just remember you. Check. Metallic type of bonding. I think it's chapter 3.5. Check it once more, but you should find it in the 3rd chapter where we talked about different types of chemical bonding. And we do not remember that in here. It's related to metals, but we already talked about that. What I like to do is talking about steel once more. Steel is one of the most important metals in industry, in the steel industry. So what we find in nature is not elementary iron. Why not? It is ignoble. It's not very noble. So what do you think can we find in nature? Instead of elementary iron? Well, if you are in nature, mostly we find oxides. Which type of oxide do you expect when we talk about iron? What is the formula? Yeah, it's one of these possible oxides, but think about more easy, FeO. Iron, we know iron 2, we talked about iron 2. And so FeO is one of the oxides which can be found in nature. And what we try to create is elementary iron. What we like to have is pure elementary iron. So what do we have to do? We have -2, so +2 here. and 0 here. So what happens to the iron? When we come from +2, it's a reduction. So we need electrons. Do you know from where the electrons are coming in the steel industry, typically? Yeah, they use carbon. So different forms of carbon, coal. And one of these intermediates in there is the carbon monoxide, CO. And what happens is, what is the oxidation of carbon in the CO? +2. And what happens to the carbon in the CO? Yes, so we create CO2. What's the oxidation number of carbon in CO2? +4. So what is here happening from +2 to +4? Is it an oxidation or reduction? So here we have the oxidation, here we have the reduction. Here we spent 2 electrons, here we need 2 electrons. So that's fine. Now balance the overall reaction is already balanced. We have 1 iron, we have 2 O, and we have 1 carbon. That's the main reaction. But of course, this is just the overall end up view on this system. We start with carbon. What we have is coal, pure carbon. And when we oxidize carbon only partially, we create carbon monoxide, not carbon dioxide. So we need, because we have O2, we need 2 carbon, then we have 2 times carbon monoxide. This is a delta, the heat of the reaction at standard conditions is -221 kilojoule over mole. When you read this, is it an exothermal or an endothermal reaction? Exothermal, quite a lot of heat is produced. In parallel, now we have even CO2 from the atmosphere or from total oxidation of the carbon in balance with the elementary carbon. And this is a balance which forms 2 carbon monoxide as well. And here, the heat of the reaction is plus 173 kilojoule over mole. Is this exo or endothermal? Endothermal. This is only happening at very high temperature. But in the steel industry, you maybe have heard it's steel cooking. They say we have to cook the steel. They have liquid iron. What you're expecting is very high temperature created by these reaction. Partially, it is even carbon plus O2 forms CO2. I don't know the heat of the reaction, but it is negative. So partially total oxidation, that's a partial oxidation, and that reaction is called the boudoir balance. Here, this one is the boudoir balance. And this was found by Mr. Boudoir, And this is an important balance in the steel industry. First of all, we need the CO for the reduction of the iron oxide. But you have to be careful. Carbon monoxide is not healthy. It's poisoning, because if you inhale it, you die. The concentration of CO must be below 30 parts per million in the atmosphere to be safe. And if you have more, you can die, because it blocks the transport mechanism in the blood for the oxygen. And that's why sometimes there were some problems in the steel industry, and Mr. Baudouin found out these things, that CO is built intermediate. So the iron is oxidized, the carbon is reduced. When you calculate all these different reactions, not caring about the last one, then you can say the overall total is, we have 2 FeO and pure carbon, which is added to form CO. And then we have elementary iron 2 times and CO2. And the delta is 100 of the reaction at standard condition plus 138 kilojoule over mole. That's the overall reaction. 138 is here the overall reaction and enthalpy. So it is endothermal. So we need carbon to reduce iron. And we produce CO2. Now, if you think on that, that's typical in Germany, in the northwest or in the west of Germany, near Duisburg, Colonia. We call it Ruhrpott. In Germany, it's in the area where the main steel industry is located and was located in the past. There, they had quite a lot occurrence of coal. That's why they placed the steel industry there, because they needed huge amounts of coal to produce iron and steel. But what's the problem? The problem is here, the CO2, that is a greenhouse gas. So now think about what can we do to replace carbon in the steel industry for the reduction of the iron oxide. So we need another element. Yes, hydrogen. Very good. Hydrogen, if you use hydrogen, the hydrogen gas is oxidized, it forms water to produce iron. And of course, that is not CO2 producing. The hydrogen must be green, so it has to be produced via electrolysis, not from fossils, because then we have CO2 emissions from the fossil way of hydrogen production. So in future, green hydrogen instead of carbon. So as a kind of homework, please create the overall redox reaction for steel production instead of usage of carbon with hydrogen. So you have the iron oxide, and you have to produce elementary iron using hydrogen. So homework. Create the overall redox reaction using green hydrogen instead of carbon for steel production. Please think on that. This is a good exercise to handle redox systems and to calculate everything in that area. Take it seriously. If you are able to do that, it's a good preparation for the exam. Next week, we will end up with the chapter metals and have some further singular topics to talk about. And most of the content will be done before Christmas. After Christmas, we will have some repetitions, maybe a few things to add. And so it's a good time to prepare everything over Christmas holidays. Thank you. See you next week.